For any kind of general reaction where capital A and capital B are making capital C and capital D, and the little a, little b, little c, little d, those are the coefficients, the stoichiometric coefficients for the chemicals. Anyway, for any reaction like that, you can write what's called an equilibrium constant, and it gets the symbol capital K. And K is always equal to the products divided by the reactants. And all the products and reactants are raised to their stoichiometric power. So you can see there for the equilibrium constant K, on the top part there you have capital C in square brackets, that means moles per liter, and it's being raised to the C power, little c. Capital D in square brackets, that's the moles per liter of compound D, it's being raised to the D order there. And then in the denominator, the bottom, you have capital A to the little a power, capital B to the little b power. That's how equilibrium constant works. So an equilibrium constant is going to be nothing more than a number, all right? And the number will actually have a lot of information that we can use to describe the equilibrium. K values are always positive, they're never zero, and they're never negative. K is independent of your starting amounts, so you can have any amounts that you start with and it will still work. However, K is temperature dependent. And the magnitude of K, how big it is, will help us to understand the extent of the reaction. Like, do you have just a little bit of products or a lot of products? And if you do know K, there's lots of stuff you can do. You can predict the concentrations of products and reactants and all kinds of other stuff. So we're going to explore in this section how to figure out what K can be. So here's a question you might see. It says, which of the following is the correct form of the equilibrium constant for the given reaction? And you can see in this reaction, we have two SO3s in equilibrium, double-sided arrows, with two SO2 sulfur dioxides and an oxygen, O2. And there's different versions of K. Okay, so the punchline here is that K has to be products over reactants. And the products here are SO2 and O2, and the reactants are SO3. So you can see, for example, like in question A, you do have the products, SO2 and O2 in the numerator and SO3 in the denominator. So that's at least that part of it. However, the one part that A is missing is you have to raise each of the chemicals to its stoichiometry. So the SO3 should have a 2 next to it because there's a 2 by the SO3 right there. And also the SO2 should have a 2 next to it because there's a 2 right there. The O2 would be raised to the first power because there's an invisible 1 right there. So anyway, if you look through those long enough, then you'll see that answer B there has the products, SO2 and O2 in the numerator. It has SO3 in the denominator. But in addition, you're raising the SO2 to the second power because there's a stoichiometry of 2, and the SO3 is being raised to the second power 2. So products over reactants, raise all the chemicals to their stoichiometries, good to go. This isn't really anything you have to know. However, I know that some of you are kind of curious about this, so let me spend just a little time and talk about the origin of capital K. And capital K, the equilibrium constant, stems from the rate constants little k from the kinetics chapters. So as an example of how this works, let's take two NO2s going to N2O4, all right? And you could have a rate for the forward reaction, and rates, as we talked about in kinetics, are usually the reactants. Most of the time, if it's an elementary reaction, the stoichiometry and the power are the same. So NO2 is a second order reactant, and we'd have some kind of K sub F representing the rate constant for the forward reaction. And you can do the same thing for the reverse reaction. Now N2O4 has a 1 by it, so it's raised to the first power. It's probably an elementary reactant, and we'll have some kind of K reverse for the reverse reaction. Well, anyway, what you can do, if this is at equilibrium, the rates are the same, all right? The forward and the reverse rates will be the same. So you can let KFNO2 squared equal KRN2O4. You can rearrange the expression in order to have products over reactants. So in this case, it would be N2O4 over NO2 squared. KF over KR is just this product, if you will, of two different numbers. So equilibrium constants K are nothing more than basically the rate constants for the forward reaction divided by the rate constants for the reverse reactions. So again, this is nothing you need to know, but big K is related to little k's, all right? And just like we saw little k's are temperature dependent, big K's are temperature dependent. And that's where this all comes from. It is important that you use capital K for equilibrium and small k for rate constants. You don't want to confuse anybody and stuff. But anyway, this is the origin of it. And if you feel like that cat, like, what? Whatever? I don't know. Anyway, I totally understand. But anyway, there's a relationship between kinetics, rate constants, and equilibrium constants. As long as you kind of remember that in the back of your mind, you're good to go. The textbook uses Q a lot more than I would, and I just want to talk about it. Q is really used when you're in an experiment and you're not sure if you're at equilibrium, and we'll talk about Q. Most of the time that the textbook uses Q, I would just use K, but there's nothing wrong really with using Q. It's a little awkward. I'll talk more about this later when we talk about Q, but if you see a Q in the textbook, just assume it's a K, all right? I'll talk more about this in a little bit, but if you look at the textbook, that can be a little confusing. This is a reaction where hydrogen, H2, and iodine, I2, are reacting to make two hydrogen monoiodides. And what we see here, if you look carefully, the line that starts in the upper left and kind of goes down to the lower right with H2 and I2, there's both a red line and a blue line, and they're right on top of each other because every 1 mole of H2 is going to need 1 mole of I2, so they're going to have the same behavior. And they're both reactants, so they're both going to be diminishing over time. They're going to go down. Now, on the other hand, HI here is the product. HI is going to be appearing, so that picture, which is the concentration on the y-axis, that picture shows correctly HI getting bigger and bigger and bigger. But finally, you get to some point where the relative amounts of HI and H2 and I2 are about the same. And that's where chemists consider equilibrium to have been achieved. If you pick a point to the right of the red line I just drew there, that's going to be equilibrium. If you did it to the left, you wouldn't be at equilibrium yet. Like your HI wouldn't be big enough and your H2 and I2 would be too big. But this is what chemists are thinking about when they say it gets to a kind of a constant rate. You want the HI amount to be relatively the same, and you want the H2 and the I2 amount to be approximately the same. So in the equilibrium region, when you want to write an equilibrium constant, that equals products over reactants. There's a 2 in front of the HI, so we would write HI squared divided by H2 and I2. And again, the square brackets means moles per liter. Now, the value of this equilibrium constant has been studied quite a bit, actually, and the value is 55.3. So big K is usually a unitless quantity. You can put units on there if you want to, but it's honestly kind of tedious and not very helpful. So scientists usually just report the value of K, not anything. Remember, K can never be negative or 0, but it can be anything larger than 0. This is 55.3. In this reaction, we're taking a compound that's NOCl, nitrogen oxychloride. We're placing the nitrogen oxychloride in 2 moles of it in a liter flask. And at equilibrium, we find that once everything settles, we end up with 0.66 moles per liter of nitrogen monoxide, one of the products. We can actually use this information to calculate the value of K. So if you need to find the value of K, almost always you'll set up what's called an ICE table. ICE is an acronym, but to build the ICE table, you want to have reactants and products. So you can see right there, I've got NOCl and then NO and Cl2. And sometimes if you want, you can even put the stoichiometries next to them. Just kind of helps out. So there's a 2 in front of the NOCl and a 2 in front of the NO. You don't have to do that, which I didn't here, but I'll do it anyway just for the heck of it. ICE stands for initial for I, and initial is literally how much you start with. So in this problem, we had 2 moles in a 1 liter flask, or a molarity of 2.00 molal. That's the initial NOCl. And we didn't have any NO or Cl2, so they're just empty. Now, C stands for change, and E stands for equilibrium. So you can see what we have here, ICE, initial change equilibrium. Equilibrium is going to be important, and the other piece of data we have on this reaction is the 0.66 moles per liter of NO. So right now, we're missing quite a few values, but this gives us a good chance to talk about what ICE is all about. First of all, it's the equilibrium lines, the equilibrium concentrations that we will use to calculate K. So once we know all those values, we'll take NO squared times Cl2 and divide by NOCl squared, and that'll allow us to find K. But we're not quite there yet, as you can see, because we're missing some points. Now, the change of the reaction shows how much the NO in the middle column goes between the initial point and the ending or equilibrium point. And you can probably see that NO is increasing by 0.66 moles per liter. Remember, there was nothing to begin with, and at the end we had 0.66 moles per liter, so NO changed by 0.66 moles per liter. Now, earlier I said the stoichiometries can be helpful, and this is one place where it can be super helpful, because we can easily calculate how many moles per liter of chlorine were also created. And we do that because 2 moles of NO are created for every invisible 1 mole of chlorine. You can see it better up here in the balance reaction, 2 NOs for every 1 Cl2. So you could write 0.66 moles NO per liter. You could then have 2 moles of NO on the bottom and 1 mole of Cl2 on the top. Kind of like a grams, moles, grams thing, but just the moles to moles part. But hopefully you can see that if 2 moles of NO are created, that means 0.33 moles per liter of chlorine were created. So notice here that there's a 2-to-1 ratio in the formula, and the concentration of NO is twice as much as the concentration of Cl2. They're going to be made at the same time. There's a 2-to-1 ratio. That's where that came from. So at equilibrium, the amount of Cl2, 0.33 moles per liter. But we're not done yet, because the NO and the Cl2 had to come from something, and they're coming from the NOCl. So again, notice how there's 2 NOCl's being used up for every 2 NOs that are being made. Well, if NO and Cl2 are increasing, their products, they're being made, they have to come from something, and they're going to come from the NOCl. So if there's a 2-to-2 ratio of NO to NOCl, and NO is being made, that means the NOCl has to go down by 0.66 moles per liter. So NOCl is going to be going down by 0.66, while NO is going to increase by 0.66, and Cl2 is going to increase by 0.33. And I want you to stop just for a second and look at that change table, because there's a 2-to-2-to-1 ratio in that change line, similar to the 2-to-2-to-1 ratio you see up here in the balanced reaction. So the change line is very susceptible to stoichiometry. We had a 2-to-2-to-1 ratio in the balanced reaction, and in the change line you can see we have 2-to-2-to-1. It's 0.66, 0.66, 0.33, but same idea. But the other thing is that notice how the reactant is decreasing. It's going to have a negative value because that's the part that has to be used up in order to make the NO and the Cl2. So that's kind of cool too. Now, to finish this table off, the NOCl at equilibrium will be the initial amount minus the change part. That's going to be 1.34 moles per liter when you do the math. So initial, and then use the change to figure out what the equilibrium is, you're good to go. So at equilibrium, in the next slide, we're going to use this line right here, the equilibrium values, to calculate K. It'll be the products over reactants. We'll raise the NO and the NOCl by 2 because that's what their stoichiometry is, and we'll plug those numbers in to calculate K. But at the end of the day, just remember, the change line will reflect the stoichiometry perfectly. And since we have a 2 to 2 to 1 ratio in the balanced formula, that is reflected in the numbers, like absolute value, all those numbers, 0.66 to 0.66 to 0.33, that's 2 to 2 to 1. However, reactants will go down. In this case, that's why there's a minus 0.66 under NOCl, and the products will both appear, positive 0.66 and positive 0.33 respectively. So here's the non-messy version, if you will, of that ice table. Much better handwriting than I can use, but hopefully you get the idea. Again, I want you to focus on big time the importance of the change level. The change line there reflects stoichiometry. So 2 to 2 to 1 and NOCl to NO to Cl2 in the balanced reaction is reflected here. 0.66 to 0.66 to 0.33, that's 2 to 2 to 1. There is also, if you will, a line of demarcation between reactants and products. And so in this case, the reactant is going down and the products are going up. And this will always be the case too. Like products will be up and reactants will be down, or you can have it reversed like we'll see, i.e. sometimes products will go up and reactants will go down. But anyway, it's always going to be this line, and on one side everything is positive and on the other side everything is negative. So now that we have the equilibrium concentrations of all reactants and products, we're going to use that E part of the ice table to actually calculate the value of K. And K is going to be products over reactants. It's going to be the NO quantity squared, because of the 2 in front of the NO, times Cl2 divided by NOCl squared. Again, that squared also comes from the 2 in front of the NOCl. So you literally plug those values in, 0.66 squared times 0.33 divided by 1.34 squared. Bam! 0.080 is your equilibrium constant. So pat yourselves on the back. You just calculated your first K. Can your heart stand the strain? When you're writing equilibrium expressions, you do not want to include solids or liquids, and that's really important. So basically in an equilibrium constant K, you will only write gases and aqueous solutions. So for this reaction, sulfur and oxygen making sulfur dioxide, notice the sulfur is a solid, so you'll leave that out. This K would be just the SO2 divided by the O2. For water, that's going to be the number one reactant that we will not include in equilibrium constants quite often. So in this reaction, which is ammonia and water making ammonium and hydroxide, your K value would be ammonium times hydroxide divided by NH3, but you won't put the water in. And this is a good time just to remind you that NH3 is ammonia, NH4 plus is ammonium, and they're quite different. The reason for the solids and liquids not being placed in is often referred to the fact that solids and liquids have an appreciable density. And if you change the concentration, it's like changing the grams over volume, which is basically molarity, which is basically density. All right. And so that's why they feel that there's no real appreciable change for solids and liquids. I don't care if you believe it or not. I'm not even sure I believe it sometimes. But the important part, once again, no solids and liquids in equilibrium constant expressions. So here's a reaction. We have potassium metal. Potassium is a solid, K solid, reacting with water to make KOH and H2, and you want to have the appropriate equilibrium constant expression. Well, the big punchline here, of course, is that you don't want to put solids and liquids in your equilibrium expressions, but aqueous parts and gases are okay. So if you look at this, the K is a solid, so that's not included. Water is a liquid, that's not included. So notice that everything on the reactant side is not going to be part of the equilibrium expression. So if you run into this, just think of that as a big 1, all right? It's not like you don't have it, but it's just that nothing shows up. So in this problem, the products will be KOH squared times H2, and that's okay. And in the denominator, everything cancels out, so you would just put a big 1 or an invisible 1. And that means answer E will be the correct version, all right? So if everything is a solid and liquid, just put a 1 right there. It's no problem, but you still have to include the KOH and the H2. There's more you can do with equilibrium constants. This is sulfur plus oxygen making sulfur dioxide. Let's call the equilibrium constant for this one K1. It would equal SO2 divided by O2, but again, don't put the liquids, or in this case solids, in the equilibrium expression. However, let's say that you wanted to add 1/2 more oxygen, and you wanted to make sulfur trioxide instead of sulfur dioxide. All right, no problem. K2, products divided by reactants. So for K2, the second expression, it would be SO3 divided by SO2 times O2 to the 1/2 power. So raising the stoichiometry in this case gives a raise to the 1/2 power. That's like taking the square root of the O2, by the way. Well, let's say that your instructor came around and said, why don't you just figure out an overall K for all of this, i.e. what would be the equilibrium constant for sulfur reacting with 3/2 O2 making sulfur trioxide. So the sulfur dioxide, which was a product in the first one, and the sulfur dioxide, a reactant in the second one, are essentially canceled out. Well, the overall K then for this reaction would just be sulfur trioxide divided by O2 to the 3/2 power, and when you do the math, it's actually equal to K1 times K2, because again, the SO2s will cancel out. In K1, it's a numerator SO2, and in K2, it's a denominator SO2. And the O2 and the O2 1/2 combine to make O2 3/2, the joys of these exponents, so you end up with sulfur trioxide divided by O2 to the 3/2 power. Your instructor says, hey, fractions are lame. Get rid of them. Multiply everything through by 2. So you've got the old K, which is sulfur trioxide divided by oxygen to the 3/2 power. But your instructor is being mean, I guess. So instructor says multiply everything through by 2. Okay, no problem. So do it. So the new K is going to be SO3 squared, because now there's this 2, and it'll be O2 to the 3rd power. However, if you look at this one long enough, the old K, if you would square it, that's going to give you the new K. So SO3 squared would give you SO3 squared, which is what we see. And the O2 3/2 in the denominator squared, the 2's will cancel out. You'll end up with O2 3. So if you multiply a reaction through by 2, you raise the K value by the same number. So if you had to multiply a reaction through by 3, you would take the old K and take it to the 3rd power in order to find the value of the new K. Kind of a handy little trick there. If you change direction, sulfur and oxygen making sulfur dioxide, and then decide to change it to sulfur dioxide making sulfur and oxygen, you can absolutely do that. Remember that these are reactants going to products and products going to reactants. Well, if you compare the old K to the new K, they're essentially the reverse of each other. All right. So the old K had oxygen in the denominator, and now in the new K, oxygen is in the numerator. So if you flip a reaction, you take the inverse of your old K. So 1 over the old K equals the new K when you reverse it. It's pretty chill. There's a handout down there called Manipulating Equilibrium Constant Expressions. I encourage you to check it out for more details as to how this works. But these are things that can just make your life a little bit easier. Here's a reaction where N-butane is in equilibrium with isobutane. And these are organic molecules. We'll talk about them at the end of the term. But the equilibrium constant K equals 2.5. So the question, what's the value for the reverse reaction, which would be isobutane as a reactant going to N-butane? Well, to get the value of the new K, you would take the inverse of the old K. So since these reactions are literally flipped, the new K will be 1 over the old K, 1 divided by 2.5. And if you throw this in your calculator, 1 divided by 2.5 is 0.40. That's going to be the value of your new equilibrium constant.